However, when Professor Oersted repeated the experiment, this time with the needle parallel to the conductor, and the switch was closed, the compass needle reacted instantly. So it seemed obvious that electricity and magnetism were somehow related. As a result of Oersted's experiments, French physicist André Ampère made a detailed study of the magnetic field about a conductor carrying a charge flow. Using iron filings, he demonstrated that there was a magnetic field around the conductor. The pattern formed by the iron filings created a series of concentric circles. Depending on which way the negatively charged electrons flow through the conductor, the magnetic field around the conductor will be in one of two directions. With the electrons flowing this way, the magnetic field around the conductor is in this direction. Reversing the flow of electrons doesn't affect the shape of the pattern, but it does affect the direction of the field. Reverse the electron flow through the conductor, and the magnetic field direction will reverse as well. Our left hand gives us a convenient method for correctly predicting the relationship between the direction of the magnetic field around the conductor and the direction of electron flow through the conductor. This is the left-hand rule for conductors, and it states that if the left hand is placed around a conductor with the thumb pointing in the direction of electron flow, the fingers will curl in the same direction as the magnetic field. Reversing the current means that the thumb must now point in the opposite direction. Although the fingers now curl the other way, they nevertheless indicate the new direction of the magnetic field. Of course, if the flow of charge is interrupted, the magnetic field collapses immediately. What happens to the overall shape of the magnetic field if the conductor is bent into a loop? Let's turn the current on again and find out. If we apply the left-hand rule at different points along the conductor, we can map the magnetic field around the loop. Notice that the shape of the field resembles a donut. But if a number of identical loops are added, the resulting figure is called a helix or coil. Looking at the coil in cross-section, we'll represent electrons flowing away from us as X's. And here at the bottom, electrons flowing towards us as dots. Applying the left-hand rule for conductors to each turn of the coil, we can begin to build a picture of the magnetic field around the coil as a whole. Since the distance between the turns of the coil is very small, we might think that the fields would overlap like this. But this is not the case. Magnetic fields do not overlap. Instead, the field of one interacts with the field of the other to produce a combined field like this. If we examine the area between two of the turns, we can see that the two interacting fields effectively cancel each other. This field interaction occurs between each of the turns of the coil, resulting in an overall field which surrounds the turns and resembles a somewhat flattened oval. The same oval pattern is produced at every point around the coil. And it's the merging of all these ovals that forms the magnetic field for the entire coil. Since the field direction of each oval is the same, then in the center of the coil, cancellation does not occur, and that portion of the field is very strong. There is also no cancellation outside the coil, but because the field is spread out, it is much weaker here. The relationship between the direction of electron flow in the conductor and the direction of the field in the center of the coil is given by another left-hand rule, the left-hand rule for coils. This time, the fingers curl in the direction of electron flow, and the thumb points in the direction of the field within the coil, or to the end of the coil that acts as a north pole. The fingers curl with the current, and the thumb points north. If we compare the magnetic field of the coil with the field of a bar magnet, we can see that the shapes are nearly identical. Each has a north and south pole.